Okay, so in the previous modules, we've talked about um, solving equations using the unit circle. We used our calculators to solve. All right, now we're going to go over one final technique here in our solving equations kind of journey. All right, so we're going to be solving using some factoring techniques. All right. Now, mainly two in particular. All right. The first one is the greatest common factor. So we're going to use the greatest common factor to solve an equation. Right. So this is probably something that you've seen in an algebra class, or probably an arithmetic class of sorts. So if you need a refresher, there is a video on the preamble looking at in algebra, the greatest common factor, but I'm going to look for it strictly in terms of trigonometric functions. All right. So for example, let's say we wanted to factor completely. Let's say we had the expression tangent squared x cotangent x minus tangent x cotangent squared x. Okay. All right. And then from here, we could say, all right, what is the greatest common factor, right? So we're looking for factors common, right? The keyword common in both of these, right? Now keep in mind the notation here when we have a exponent, tangent squared x, that's equivalent to tangent x times tangent x. Okay. Excuse the lighting there for a second. All right. Okay, so what do both of these have in common? They both have tangents and cotangents, right? This one has a square tangent, but this one only has a tangent. So I choose the one that they have in common, which is simply 1, right? If I choose 2, this one doesn't have 2 factors of tangent. So I just choose 1. Right? What else do they have in common? Right? Well, I notice they have a cotangent. Again, this is cotangent squared. This is just cotangent, so take the lower number of factors of the two. And we have both of those in common. All right. Okay, so here we have what's the resulting expression here, right? So we've took away one of these factors, but there's still one left. We've factored out a factor of cotangent x. This one's only 1, so there's no more cotangent factor there. All right? Becomes 1, but again, 1 times tangent x, simply tangent of x. And then over here, right, we factored out one factor of tangent x. All right? So then it's just 1. Right? No need to write it for now, because we have excuse me, a factor of cotangent squared, but I factored 1 out, so we have cotangent x. Okay, and now it's factored completely. All right, so here, all right, if you distribute, you should get back the original. Well, in this case, you do, but that's one way to check, right? If you do some distribution, you should get back your original expression. All right, let's do one other example here, looking at the greatest common factor. All right, so the greatest common factor, here we have secant squared x cosecant squared x minus secant of x. Okay. Excuse me. All right, looking at this, we see, all right, what do they have in common? All right, this has secant squared, cosecant squared. This has secant. So remember, it has to be common in both. So the only one I see in common there, the only factor is a secant x. And it's to the first power, right? Because we just take the lowest of the powers. This one's 2, this is power 1. So now what's left? Here, there's one factor of secant x. This I didn't factor out, so it remains the same. All right, now here, 1, and we are going to need that because there's no other factor, so you have to make sure that that 1 is there. So when you do distribute, you get back the same original expression. Okay, so that's how we kind of factor these trig expressions, looking for the greatest common factor. Now, another factoring technique that we're gonna come across is factoring trinomials. Okay. All right, so in this case, trinomials are something that looks like this. Right, now this is a quadratic trinomial. Okay, now what I'm gonna show here is that there's nothing that is different in terms of the factoring of something like this as opposed to something like this. All right, now this factors into this. All right, and again, right, this is something that we learned in algebra. Again, if you need a little refresher, there's a video in the preamble of our module that can go over kind of different techniques. I'm sure the factoring, at least, I've seen whatever numerous techniques that work in factoring trinomials. I'm sure you're probably familiar with one, and you feel free to use whatever you're comfortable using. Okay, so in the same form, the way we factor this, this also factors. It's what's called a quadratic form. In the same way, right? Now, if you're having trouble seeing this, one nice thing that you can do, or excuse me, one thing that you can do is you can make a substitution, right? If you're still having trouble seeing the quadratic form, you could see, all right, well, what if I just let y is equal to sine of x, right? Then what you see here is sine of x squared sine x minus 1. And then when you make the appropriate substitution, now we have something that's of quadratic form. And if you're more comfortable factoring this, and then the last step would be to substitute back in, right? Don't forget that. Okay. All right. So that's what would be how we would factor, right, some of these trig expressions. Okay. Now, what we're going to encounter is trig equations that are of quadratic form, which I've been speaking about. Now, there are trig equations, they're not quadratic, right? That's a very specific form of an equation, right? Quadratic, a graph looks like a parabola, right? The quadratic form looks something like this, right? Where A, B, and C are numbers, right? And A is a non-zero, right? Because if it were zero, then it's not a quadratic, right? It'd be some kind of linear function. Okay, so some of our trig equations will follow this form, where we have our term squared, then here linear, and see now sometimes it's hidden in the sense like it could look something like this. Now, right away, when you look at this, you're like, oh, this is not a quadratic equation or a quadratic expression. And you are correct, it is not. All right? But it does have a quadratic form. It does follow this, where we have a squared, then we have a linear term. Right? In this case, we have a quartic to the fourth power, but then we have half of that power here, and then a constant term. Right? So what happens, what it turns out is, you can make a substitution here. Squared. All right, so then that means we have x squared squared Here I'm just rewriting this so we could see how our substitution yields our quadratic form, right? So now x squared I said was y. X squared y, right? This is y, and then squared we get y squared plus 2. All right? And now we have a quadratic, and that could be factored into this. Okay? Outer inner is -1 minus 2 gives us -3y. Last one is plus 2. And again, in the end, don't forget to substitute back in. Okay. All right. All right. And then now we can apply the same idea here if we did see something like this. If we had like cosine to the 4th power of x minus 3 cosine squared x plus 2. Right? That same idea, we could see that it factors. All this is just going to be cosine squared x minus 2 times cosine squared x minus 1. And it can factor like that, right? Using a similar substitution, we let y be cosine squared x. Okay? All right. So those are ways to factor. Some special other factoring kind of techniques that might pop up is a difference of squares. Where we have two squares, x squared minus a squared, that simplifies to x minus a, x plus a. All right, now this only works for a difference because when we do the distribution, the first, outer, inner, last, what you'll notice is the middle term, ax minus ax, cancels out. And this nice property only happens when we have a difference of squares, right? So if we have something like, let's say, x squared minus 4, that's equal to, the square here is 2, right? 2 squared, x plus 2, right? And again, there's nothing here that is no different than, let's say we had cosine squared x minus 1. Right here, squared is cosine, and 1 is a square, right? So here we have cosine x minus 1, cosine x plus 1. Okay, so these techniques we can apply to our trig functions as well. Right? Now the reason we want to have these in factored form is because we're going to take an advantage here of a very nice property of numbers. Right, the zero property. So if we had any number of factors here, right, 12, 4, 3, 18, 0, right, I could have any number of factors, right? Now if you're looking at this, immediately you should know what the result is, right? Once you see a 0 here, that destroys everything, right? Everything, the solution to this is 0. No matter how many numbers, how large those numbers are, it's just going to be 0. Okay, so this property here of these factors and the number 0 and the factoring of, or as many factors as we're multiplying, that the result is going to be 0. We're going to take advantage of that when we do our when we're solving these equations. All right. So let's do a basic one, a basic trig equation without any factoring. Let's just say I had sine x times cosine x, and that equals to 0. Okay. All right. So I have two factors, sine of x and cosine x. Now when I multiply them, I get 0. Right, now again, the only way that happens is if one of those factors is 0. So this can happen one of two ways, right? I have two factors, right, with some value of x unknown. So the only way that this statement is true is if sine of x is equal to 0 or cosine of x is equal to 0. Right? And again, these happen at different values for x, so I need to check for both of them. All right, and let's say I just want solutions on the interval 0 to 2 pi. All right, well, sine of x is 0. These are quadrantal angles, the first angle being when x is 0 or x is equal to pi. All right, if we look here, right, the y value is 0 in our unit circle, and then over here. Okay, and in between 0 and 2 pi. Or when cosine x is equal to 0. Now we have equations that we solved when we first started solving equations, right, using our unit circle. Cosine x is 0, again at quadrantal angles. In this case, x is pi over 2, or x is 3 pi over 2. Okay? All right, and at those values, right, the cosine is 0, and that would make our original equation true. And that's it, right? Those are the only values in between 0 and 2 pi where we get a true statement, right? Now again, not both of them do not have to be 0, right? When we have a factor, multiply just one of them, right? Similar to this right here, right? And you see, we'll test one of these, right? Let's let x equal to pi. We get sine of pi times cosine pi equals to 0, right? This is 0. This is -1. But again, right, 0 times any number. So that checks out. Okay, so that's the approach we're going to take in this module. We're going to look at setting an equation equal to 0 and trying to factor it. Right? I would always encourage you when you're factoring, factor out the greatest common factor first. Right? Do that. All right. That should always be a couple of tips here. Find the greatest common factor first, if it has one, right? Sometimes, right, there is no greatest common factor, or the greatest common factor is 1. I shouldn't say there isn't one. 1 is always a factor of any expression. Okay. Something else you should do is never divide by a variable. Okay. So for instance, when we had here, what you don't want to do is divide by sine of x, because that would completely eliminate these two solutions. Okay, remember, x is unknown, so it can be 0, or the expression where x is can be 0, so you don't want to go and divide by 0, right? Because that's, I don't know what division by 0 is. Right, it's undefined. Right, and especially if we have 0 over 0, I definitely don't know what that is. All right, so never divide by a variable. And then also, right, try determine if it is a quadratic form. Right, sometimes it's easy to spot, it's just a square, but sometimes it might be that 4th power, 2nd power, sometimes even 6th power, 3rd power. That would also follow the quadratic form. Okay, so here just an introduction. In the future videos, in the next videos, we're going to look at actually solving some more involved trig equations using these techniques.